Hello everyone, my name is Yoongi Soon and this is my demo presentation for my final year project. The title of my final year project is Detection of Advanced Persistent Threat using ANFIS and Correlation Analysis. My supervisor is Dr. Anazida Pindi Zainal. So an overview of the proposed solution that I have here. There are three phases. Phase 1 is to develop the APT detection system using ANFIS, Adaptive Neural Fuzzy Inference System. And phase 2 is a correlation module where I correlate the different APT stages that is classified by ANFIS to form one single APT scenario. And then there is a third phase where I measure the performance of the detection system. So this is the demo flow. I will show you from the beginning the data, the feature selection, then how I use MATLAB to develop and train the ANFIS, and how I test it, and then phase 2 about the correlation module, how I implement the correlation rules, and also how I construct and visualize the attack timeline with Plotly. And the last phase is how I compute the measurement of metrics that is planned to measure the performance of the detection system. So first of all, this is the original data set that I'm using. This is a synthetic data, APT synthetic data by Garfields. So I'm using SQLite. This is a database file, so I'm using SQLite Studio to open this. This is how the original data looks like, and then I export it to a CSV file. So here, this is Excel, and then here is my feature selection Python script where I do my feature selection and engineering. So as you can see, here it first of all reads the CSV file that I exported from the database SQLite, and then I drop some unnecessary columns like the timestamp and other stuff, and I hot encode the IP addresses so that I can do my feature selection, and also hot encode the stat. This is the first feature selection that I did, univariate selection using select k best class. So let me run the script here. This is a Jupyter Notebook extension. I'm using it in Visual Studio Code here. So the first test is this: select k best class classifier, where I classify how good the feature is that can be used to train the model. So this is the second feature selection using feature importance extra tree classifier. Also run this, and I get the graph that tells me which feature is good for training. And the third one is a heat map correlation. So this is basically a correlation heat map that tells me which features correlate to which feature. So we are just looking at this stack, and this is just the same one, but this is only showing the stack correlation. So once I've selected my features, the 4 features I have, I proceed to process the data. So this is the data preparation part. So first thing I did was again encode the stack, then I split the IP addresses into 4 parts each by subnet, and then I drop those unnecessary columns that I don't need for training. Then I split the data into test and train test split, and then I normalize the data. So let me run this script here. Okay, so first I import the graphics dataset. Which is this one. This is the dataset that I import. Then I encode the stack column. I split the IP addresses by its subnet. Then I did the train test split. This is 70 and 30%. I normalize the data and I output the data. So this script basically helps me to clean up the data for me to prepare in a train and test split so that I can use it to train my data. So just an example of how it looks like. So here you see the test and the train data that I have. So this is how it looks like when I feed into my ANFIS later on. These are all normalized. These are the output. This is the output column. This is the input. So each IP address is split by subnet. So one IP address, you have 4 columns here with the ports. So total of 10 input features and 1 output, which denotes which APG stage it is. So this is my training data. So now with the training and testing data all prepared, I can move on to train my ANFIS. So first thing, this is a MATLAB 2018 academic use. So I import the train and test data here. This is in a DAT file format. Then I generate the initial fuzzy inference system for me to train with neural network later on. So this is the part where I initialize the fuzzy inference system using fuzzy C-means clustering, genotype. And then here is the part where I train my ANFIS. So you can see that the epoch starts with 5 epoch with an increment of 5 up to epoch 80. So it's 5, 10, 15, 20 up to 80. And this is the configuration for ANFIS. And here is the training part. This function, ANFIS function, where I put in the training data and also the configuration that I have, and it gives me the output fuzzy inference system FIS. And after that, I evaluate the fuzzy inference system to get the output, to get the stack for each time the epoch runs, so that I can use it to calculate the train error later. So basically, it feeds it with the train data, it updates the FIS, and then I evaluate the FIS to get what is output that it gets from the train data. And this is the same thing as well, but this is for test data. I feed the FIS with the test data, a different data set that the training model have never seen before. So that here is the testing part. I put in the test data, it gives me the test output. And then I save it, I write it into a CSV here. And then I also save the FIS for each epoch so that I can further evaluate and study the FIS. So here is the output, just for you to see. So here you can see the CSV file that I output for training output. This is a testing output so that I can compare the test and train error later. And this is the fuzzy inference system that I save for all the epoch and see how it progress. So when I run this, so it started by loading the training and testing data. Then it compute the cluster, fuzzy C means clustering. Then it gives me the initial fuzzy inference system, and now it starts training with epoch 5, and then it goes on to epoch 80. So here I will stop the training. So again, this is a MATLAB where I use the training data to train the fuzzy inference system, and here is the output that I have, the train epoch output and the test epoch output and the fuzzy inference system for each of these. So now with this output I can move on to evaluate my ANFIS here. So this is the Python script for me to evaluate the output from MATLAB. So again, I read, take in the input. So here I calculate the train error. So basically I take in the train output from MATLAB and compare it with the training data, and here I get the mean square error. So this is the same thing as well, but here I'm doing it for the testing data. I'm calculating the mean square error for test data, and here I'm just merging the two data together to draw this graph here. So this is explained in the presentation. This is the epoch MSE graph where I see the test error and also the train error. You can see, and this is in table form. So this is the epoch 1, and now to further analyze and also to get the different metrics and numbers, this is I'm calculating and getting the confusion matrix and also the classification report here. So when I run this, I'm getting the confusion matrix and also the classification report for each epoch. So from epoch 5 up to epoch 80, I have all the confusion metrics and classification report here. Of course, I only look at the one that is with the best result from here. Epoch 30 has the lowest test error here. So here I'm just looking at epoch 30. Which is this one. So this is a CM classification matrix, confusion matrix, and here is the accuracy and also classification report details, which I have attached it in my report. And the next thing I do is to get the area under graph of ROC. This is to see how good is ANFIS in classifying stage 1, stage 2 and stage 3, how it differentiates different classes. So this is a plot. This is matplotlib. Here you have the TPR and also the FPR, and also the score here. And this is the chart. S3, S2, and S1. As you can see, S3 has the least out area under the curve score, which means that S3 is not very good at, the ANFIS is not very good at classifying S3 compared to S2 and S1 with a higher score. So now, with all these metrics that I have on hand, here I'm outputting the best epoch data so that I can correlate and visualize. So here I'm just getting the best epoch result and cleaning up the data and putting them in a nice form table. As you can see here, this is the step, this is the predicted step or the infer step by ANFIS. So this is the source IP. Once again, I've merged it together. So before that, we have source IP 1234 and destination 1234. But now I've mapped it back to its original state so that I can use it to correlate and visualize. So now we have come to the correlation and visualization part. Again, I read the data. This is the input data earlier. And here is the attack clustering or the correlation part. So first I group them by source IP, then categorize them into full APT or sub APT, and then I can plot the timestamp against the step as in the visualization. And the order of the stages does matter here, because APT start with delivery, command and control, and then data exfiltration. This is the 3 stages in my scope, research scope, which I focus on based on the cyber queue chain model. So this is the variables that I'm using here, 1, 2, 3, signifying, representing the 3 stages. And here, this is the original data which I'm using to compare later, and this is the predicted or the infer stage. So I group them by source IP, then I filtered it. This is a lambda function, basically a function, a callback function, to test whether each group here of this source IP has the stage 1, 2, 3, and each is unique form, as in 1, 2, and 3 exists in this group, and this is the opposite one. Opposite, basically I have the NOT symbol here. So this is the same thing here, grouped by source IP, so that host A is equal to host B equal to host C, as in my presentation earlier, the correlation rule. And the lambda function, again same thing here, to check whether predicted step has stage 1, 2, and 3. So basically it means that under this source IP, this infected host, there exists stage 1, 2, and 3 of APT, and this is considered a full APT. Vice versa, same thing applies to sub APT. Sub APT basically means that APT that has 1 stage, 2 stage, but doesn't have the 3rd stage. So here I'm checking whether the stages here, the step here, does not have all stages 1, 2, 3. So I execute the script here, and they're just waiting for it to finish. Okay, done. And now I'm printing out the full APT here. So just a simple look at the data here that I correlated, you can see that this is one group, this IP that ends with 217. You can see that the step is 122, but our ANFIS model predicted 132. So this is the correlated data that I've grouped by source IP so that I can visualize later and also compare. And this is the sub-APT data, same thing here. So now is the visualization part, where I visualize it in line graph. This is basically Plotly. I use Plotly to plot the line graph, put in my data, X and Y axis, give it a title, set the color with the label, and this is the results. So this is actually interactive. I can hide which IP that I don't want to look at, or select which IP that I want to, or I can also look at the source IP, timestamp and step. So this is the original full APT attack timeline, and this is a step 1, the delivery phase, step 2, command and control, step 3 is the data exfiltration, and this is the timestamp or timeline here. So basically, one example here is that this source IP 227.161 have APT step 1 at this timestamp. Step 2 happens here after step 1, and then step 3 happens almost immediately. So this is the original data set. This is not output by ANFIS, and here we have the inferred full APT attack timeline, where this is classified by our ANFIS, the trained ANFIS by MATLAB. So same thing here, this is predicted step 1, 2 and 3, timeline, source IP, and here we can see one example is here, this IP address 253.86, predicted step 1, step 2 happens after that, and step 3 almost immediately. So this is the attack timeline reconstructed after correlation. Now with these two graphs that we can compare, you'll see that there's 15 full APT attack timeline that is inferred compared to 35 here, and later on we will calculate the matching attack timeline and how many did we correctly infer and how many we wrongly inferred. So that is the full APT attack timeline that I get to compare here, the one inferred or predicted by our ANFIS model system, detection system, and this is the original attack timeline from the data. Same thing happens here. This is for sub APT. Here I'm running the script. This will take a bit longer because the sub APT data here is much bigger compared to full APT. So this is the original sub-APT attack timeline. This is the sub-APT attack timeline based on the original data from Garfield's. This is again the step 1, 2 and 3. This is the source IP, basically the infected host. The host has been infected by APT or attacker. This is the attack timeline. So here you can see that there is a lot of APT stage 1 and 2. You can see that basically this bottom half of the graph has more line than the top half. And again, all this line is only two dots, or 1 dot, 2 dot at the maximum. 1 stages or 2 stages. It's not 3 stages, full 3 stages, because they are sub-APT. This is the original one, and this is the one inferred or predicted by our ANFIS detection system. So here you can see that stage 3 there isn't a lot that has been predicted by our stage 3. That means that, as I mentioned earlier in the ROC graph, that our ANFIS detection system is not good at classifying S3, which is data exfiltration. The reason I explained in the presentation video. You can see that S1 and S2 is still the majority here, just like the one here in the original data. And here I'm calculating the metric as I compare the original and the inferred full APT, and also the original and the inferred sub-APT. So there's a total of 15 that has been predicted full APT. Out of 15, there's 10 out of 35 that is correct, which is 29% here, and false positive of 5 full APT. And same metric for sub-APT, total of 641 sub-APT attacks, but although my detection system only detected 428 correctly, true positive is up to 69%, and false positive of 213. So that is all the demo that I have here from start to finish. So from data preparation to generating the initial fast inference system, to training and testing, correlation, visualizing attack timeline, and also computing the performance by accuracy and F1 score. So that's all from me. Thank you everyone.